So last time we derived this plasma oscillation frequencies by solving the second order Heisenberg motion, and we find this omega p, which is proportional to square root of this rho 0 average density of electrons. And that oscillations are collective motions of electrons, and it happens only when Q is very, very small or less than a critical value QC, where this approximation is valid. But for Q beyond QC, the physics is dominated by the single electron hole pair excitations, as I mentioned. So there's such a kind of a separation of the two regimes when you sum over this momentum transfer in the Coulomb potential. Okay, so we could separate this two parts of the potential in the Hamiltonian, and to emphasize the different physics behind it. Okay, so for a large Q regime, this is dominated by short-range Coulomb interactions, and for lower value of Q, less than QC, it is dominated by the long-range Coulomb part of the interaction, and it is long-range because Q is actually very, very small. And remember that if we consider the Coulomb potential as 1 over Q squared, and Q goes to 0 limits, you get divergence, right? And this divergence comes from the fact that this is the 1 over R potential, right? So there's 1 over R long tail will lead to such a divergence when Q goes 0. Remember that. However, this is what we expect when we do Hartree-Fock. This is not Hartree-Fock. Okay, so we would not encounter such a divergence, and this is a key point. Okay, so the reason why we don't get such a divergence is because of the plasma oscillation that we found. Okay, because the electrons actually do such periodic motions collectively, so they look like a collection of many harmonic oscillators, right? So each electron plays, a single harmonic oscillator, but they dance together. So it's a collection of many simple harmonic oscillators. All right? So, and we will analyze this zero-point motion of the harmonic oscillator, and the ground state of the simple harmonic oscillator shows a zero-point motion, right? So 0-point energy, epsilon 0, is actually a constant finite value, and so this contributions from this so-called potential term will not lead to the divergence at 0 temperature, because we know from the physics of harmonic oscillator that at 0 temperature, the ground state energy is actually a 0-point energy. For that reason, we avoid such a long-range part of the Coulomb interaction. So let me just explain this physics. As I mentioned, this Coulomb term in this kind of a plasma oscillation physics is actually the potential energy part of the simple harmonic oscillator. And of course, there's the kinetic energy part. Where is the kinetic energy? Well, kinetic energy is here, right? Okay, so you can consider this potential energy part of the simple harmonic oscillator gives rise to this kind of Hooke's law, right? So suppose I find appropriate coordinate qx, which describes such a motion of this density, and this Hooke's constant, this k, is actually proportional to omega p squared, where this omega p is nothing but the plasma oscillation frequency, which is exactly the same frequency of the simple harmonic oscillator that we effectively treat the system. Okay, so we know that at t equals 0, this potential energy term is just giving rise to this half of the 0-point energy, half of the epsilon 0 from your quantum mechanics. And you know that epsilon 0 of a simple harmonic oscillator is actually 1/2 of h bar omega. Remember that, right? So the eigenenergy of a harmonic oscillator is what? N plus 1/2 h bar omega, where n runs from 0, 1, 2, and so on. So suppose it's just a collection of many simple harmonic oscillator. So the ground state of that harmonic oscillator shows the energy of 1/2 of h bar omega. But this potential energy is just consisting of just half of the total energy, okay, 0-point energy. So this gives you the 1/4 of h bar omega p. And the kinetic energy part of a harmonic oscillator leads to another half of 0-point energy. So the total energy is actually 1/2 of h bar omega. So now you can see that the potential energy and kinetic energy at zero temperature of this plasma oscillation electrons would not lead to the divergence, especially the potential energy part, because this potential energy is actually giving you the divergence from the Hartree fault, but this is not divergent because of this plasma oscillation physics, because this this density of electrons actually linked to this kind of plasma oscillation physics, so it would not give you any divergence even if Q is very, very small. Okay, so the physics is entirely different from the Hartree fault because of this density fluctuations. And now you could appreciate the reason we re-express the Hamiltonian in terms of the density operator, because you won't get this, you will not get this physics if you don't express the Hamiltonian in terms of the density operator. Right? If you simply just naively express Hamiltonian in terms of the Hartree fault term, and you will get Hartree fault result. Okay? However, if you correctly represent the Hamiltonian in terms of the correct physics, then you will see this kind of correct result coming out. Right? Okay, so this is, say, this Hartree fault. This wrong result will be avoided. So let's just compare the energy between this plasma oscillation system and Hartree fault energy, especially this long-range part. Small q limit. As I mentioned, this part consists of the potential energy term and this constant term, right? This constant term, capital N, multiply this 2 pi e squared over q squared. And this is just the energy of the plasma oscillation part. How about the Hartree fault energy? So we could also compare this small q regime of the potential term from the Hartree fault, and you will get this form. This S Hartree fault is just the average density expression value, rho diagonal q, rho of q, sandwiched by this psi 0, which is the ground state of the non-interacting electron gas. Okay, so you know immediately that this term will give you a divergence, right? When q goes 0. And then clearly that the energy, if you compare this to energy, this plasma is always shows a lower energy than the Hartree fault. What's important about this this relation? Well, it tells us that this two different ground state predicted, by two different theoretical approaches, shows different free energies. So the state with the lower free energy is actually more stable. From your statistical mechanics, you know that, right? If you compare two states, whether this is a classical or a quantum mechanical states, the states that carries lower energy wins. Okay, so the ground state should be given to the state with lower free energy. Okay, so which energy is lower? Of course, it's the plasma oscillation, which proves that this physics that coming from this plasma oscillation is actually giving us a more reliable results, because this energy is lower. And this also proves that the Hartree fault energy is not a reliable result because the energy is higher. And that's complete the circle, but we're not really in the circle yet. We need to really show the screening of a Coulomb interaction. This is exactly what we are going to do. But before we derive the Coulomb screening, and we should emphasize the relevance of this calculations for the actual experiments. Okay, so as I mentioned, people have done this experiment many, many times in the past, that you strike the metal thin film by electron beam, and after the say scattering of the electron and the thin film of metals, and you could detect the intensity and energy distributions of the outgoing electrons, and they see this periodic motion, periodic patterns of this outgoing electron energy and intensity, and the period of that oscillation fits exactly perfectly with this plasma oscillation frequency that you can calculate by going through the, say, average density value of a specific metal. So you could read the corresponding chapter and sections in Flansburgh, also Kittel's second book, and also David Pine's lecture notes. I believe that this physics cannot be explained at the introductory level of solid-state physics, unless we know second quantization and we know how to apply Heisenberg equation motion. Okay, but it's not difficult to understand because these are standard many-body theory. So you have the background, so you can, of course, understand this. Great. So let's talk about the experiments. As I mentioned, this plasma oscillation physics has been observed in many scattering experiments, and this is the example that you could see in many textbooks. Yeah, so this is, say, the cartoon picture of the setup. Is made of the aluminum thin film, say 200 nanometer, say, thick, and you strike the aluminum thin film by electron beam, okay, like this, okay, and then electron will hit this thin film and then get scattered, and you could collect and detect the intensity distributions as function of the outgoing electron energies, epsilon f or EF. And from this plasma oscillation physics, the energy associated with the plasma oscillation is a unit of h bar omega p. Does this sound familiar? Okay, so this is the reason why we call, say, light a photon, because the electromagnetic wave carry energy of integer multiple of h nu, where h is the Planck's constant and nu is the frequency of your electromagnetic wave, and that is the beginning of the, say, 20th century, and we know that this is a quantum version of electromagnetic wave, which is a photon. So you could consider this is a quantized electromagnetic wave, and with the quantized energy h nu, which is h bar omega, and therefore we call electromagnetic waves photons. Okay, so photon is the quantized particle carrying integer multiple of h nu. Okay, so similarly, so we have a new excitations, collective excitation called plasma oscillations, and this is a quantum mechanical phenomena, and the basic unit in energy is h bar omega p. So we could call this quantized energy a quasi-particle called plasmon. So plasmon, like a photon, is the kind of a quasi-particle associated with the plasma oscillation frequencies, and the energy is given by integer multiple of h bar omega p, and consider this is some kind of a particle, but this is not a photon or electrons, but kind of a quantized excitation energy. Okay, so it is a quantized excitation energy, and that excitation is called plasma oscillations. So we call this quasi-particle plasmon, and we consider a collection of plasmons could occur when electron hit this aluminum thin film target. So the incoming electron beam could actually absorb or emit integer multiple of plasmon. Okay, so a wavy line represents a single plasmon. Okay, so you could either emit or absorb a plasmon, okay, before the electron actually escape from the thin film. So suppose this is the range of the thin film metal. So inside the thin film, electrons get multiple scattering and interact with plasmons many times. Electron can actually absorb or emit multiple times of such plasmon particles, quasi-particles, and they go out. Okay, so when the electron go out, you can see very clearly that the difference in energies between initial and final states of electron is actually an integer multiple of h bar omega p, isn't that? Okay, so I don't care how many plasmons that are absorbed by the electrons or emitted by electrons, that I don't care. But at the end of the day, if you measure the difference in energies of this incoming and outgoing electron, and you will get integer multiple of h bar omega p if you really plot this intensity profile. So this is the actual data. Okay, so you could plot this absolute value of the energy difference between incoming and outgoing electron, EI minus EF, and you will see the kind of a periodic patterns shows up something like this. It's very periodic. Of course, this is intensity as a function of say energy or energy difference. Okay, so delta E is the energy difference between adjacent peaks. Okay, so you will see a very regular periodic patterns of these peaks. Okay, of course the intensity, the magnitude of the intensity could vary depending on how many, say, this plasmon that you absorb or emit. Well, you could compare this kind of a delta E, which is the energy difference between two adjacent peaks. Okay, so you can compare this delta E with the h bar omega p, right? So this is the real experiments. So delta E from the experiments is about 14.8 eV, and you could also calculate h bar omega p. So that's for aluminum. This is 15 eV. Okay, so how do I calculate h bar omega p? So remember, omega p is what? Square root of, I don't remember exactly, rho 0 divided by m or something, 2 pi or 4 pi, I forgot, maybe 4 pi, right? Okay. So, and you know what rho 0 is. You can very easily check your periodic table of metals, right? Say, and you could find very easily the rho 0, the average electron density per unit volume, and then you plug in this formula and you get omega p and times h bar. When you redound, you get 15 eV. Okay, so the experimental data for this distance between two adjacent peaks is 14.8, so you get really good match. Okay, so this is remarkable because in the experiments you have no knowledge of plasma physics. I don't care about plasma oscillation. I don't know whether there exists such a phenomena. I simply just take the measurement, that's all. So of course, these peaks showed finite width, and that is because of this same thermal broadening effect, right? So you cannot, so ideally this should be sharp peaks like a spike, right? So like this, ideally, right? But of course, experiments, you are doing this measurement at finite temperature always, so there should be some broadening effect, and this is what you really see in the real data. But the important point is the distance between adjacent peaks. They are really regular, right? So you can measure the distance between any two peaks, any neighboring two peaks. You get exactly the same amount, which is 14.8. That's really magic. Okay, and then you calculate this h bar omega p, you get 15. It's almost 100% agreement. And do not forget that how we obtain such a h bar omega p. Well, we simply forget about this kinetic energy part when we perform this double commutator. Remember that, and we throw away this higher order contributions, and therefore we made already some approximations. And even so, this approximation turns out to be in excellent agreement with the experimental data. So let's look at the other material. Shows the same physics that say lithium, sodium, and potassium in EV 4.29. You see, for sodium, this agrees even beyond this integer part and go to the say the single digit below 1. Okay, so this agreement is really excellent, right? So this is, I want to tell you about the plasma oscillation physics, and this physics is actually closely related to the Coulomb screening that we will study in just a moment. So let me just remind you again this cartoon picture that I simply mentioned that many times. So you can consider this kind of motion of electrons as a result of the kind of overshooting of these different charged particles because of their either repulsion or attraction. Okay, so if there is a positive ion in the center, so it should attract this electron moving closer, but they overshoot, and then they get move away, and so on and so forth. So, but then in the meantime, you could see that maybe some, say, electron hole pair may be generated. Okay, so and that electron hole pair is actually are generated collectively, meaning so this is the real space picture, but in momentum space, you get a bunch of these electrons near the Fermi surface, which can actually get excited and then form an electron hole pair. But this is not just a single event, it consists of many, many such single events. So, the key point is that those electron hole pair excitations are closely related with one another, okay? And because they all satisfy the, say, Heisenberg collision motion, and therefore, even though we don't know where they are, but first we know they are very close to Fermi momentum. So this electron hole pair somehow know the presence of one another. Somehow they know their neighbors. Okay, so they can dance together. And also this kind of picture is actually correlated with this kind of picture that when you have more than enough excited electrons generated from the electron hole pair excitations, and you have a problem because they are overcrowded, and some of the electrons must go away in order to avoid such an overcrowded region of negative charge. And then somehow they know how they should move collectively. Either they get closer or they get further apart. So this kind of overshooting physics should actually combine with the generations of the electron hole pair excitations, and then we shall understand this within quantum mechanics. Perhaps this is the first well-known phenomena that you can understand within the quantum many-body theory. So this is the first interesting result coming from very simple naive looking Coulomb interacting electron gas. Okay, so we capture this physics correctly and accurately. So now it's time to move on to study the screening of a Coulomb potential. Remember, when we do this, say, Thomas Fermi approximations, we know that there is some cutoff, which is the exponential decay function as a function of r in front of the 1 over r factor, which cut off this Coulomb interaction. Okay, so but we need a full quantum mechanical account for such a screening. And the key point to understand this screening of a Coulomb potential is precisely this, this Hamiltonian we just formulated as a function of the electron density operator. Okay, so we will study this after the short break. Okay, everything should be crystal clear. And I recommend that you simply just imprint this picture inside your head. When you think about plasma oscillation physics, and the first thing that should come out is this cartoon picture. So this cartoon picture helps you to really understand what is going on, rather than memorizing all this mathematical formula. Of course, these formulas, equations are important, but most useful thing that helps you to understand physics is always pictures, diagrams, and graphs. Remember that. So get used to using pictures and diagrams to understand physics. Okay, so after a short break, we will go on to study the screening of a Coulomb potential. And again, we will perform perturbation theory, but this time, this perturbation is about this small density fluctuations. Okay, the small density of electrons which couple to the Coulomb potential and which lead to the small perturbation. Okay, so we treat this kind of a small density fluctuations coupled to the Coulomb potential as a small perturbation in our Hamiltonian, and then we could apply perturbation theory to estimate the second order contributions to the energies of electrons, and then we will see the screening. So as I mentioned, we could re-express this Hamiltonian in terms of the electron density operator. So now we could consider this, remember this Coulomb energy term, right? So as a small perturbation. So now we are safe because we use this correct language. So now the Coulomb potential term could be treated as a small perturbation. And we also add the external potential term U, representing the external potential energy due to the density fluctuations, right? So remember, there's a small density variation, right? So remember this thing, right? So there's a delta rho induced by this charge. So we treat these two terms, U and V, as a small perturbation. And then we try to apply the standard perturbation theory in quantum mechanics. So let's just define this U as a function of delta rho, which is induced by delta rho. And in Fourier space, this is nothing but U as function of Q times this delta rho. So the sum over P, C dagger P plus Q, Cp plus dagger P minus Q, Cp. This is nothing but rho of Q, right? Plus rho of minus Q delta. So I can put deltas because we consider the finite Q component of this density operator. So there's no rho zero here. It's just a small density fluctuations. But I consider both rho of Q and rho of minus Q because this is just a complex conjugate of each other. And so this density variation coupled to the Coulomb potential, and this U of Q is nothing but the same Coulomb potential, but the same as V, but we use different notations to just indicate that this U is really arises because of this delta rho. So this Coulomb energy or Coulomb term that we use U of Q here to really represent this Coulomb energy or Coulomb potential is coming from the coupling of a small density variation and the Coulomb potential itself. But of course, this V of Q is the same as U of Q, but here we simply just use this notation V and U to distinguish these two different parts of the Hamiltonian potential term. This V is a standard electron-electron interactions in your many body system. So now there's a real space representation of this kind of a U of delta rho is that you get some kind of a density profile, right? Density fluctuations in real space with the wave vector q here, and this actually is another form of this because delta rho, in the real space representation is simply just some kind of wave, right? So when you sum over these two Fourier components, you get this cosine term. So we treat v plus u as a small perturbation, and we do perturbation. So what kind of perturbation that we applied? So this is Rayleigh-Schrödinger. So of course there are many different conventions of a perturbation, but you could check your quantum mechanics textbooks. And I use this psi to represent the eigenstate of, say, the perturbed eigenstate, right? So this is a perturbed. And phi, the eigenstate of a non-perturbed. Okay, so a non-perturbed eigenstate is simply just the free electron gas. But the kinetic energy, acting on phi 0, is this kinetic energy part of the eigenvalue equation. So we know very well that in quantum mechanics, the perturbed eigenstate could be represented or could be expressed in terms of the summation of several terms which are made of this unperturbed eigenstate. Okay, so it's zeroth order term is, of course, it's a rough, very naive approximation that this, nothing happens. Psi is the same as phi, but of course it's not. Okay, so the first correction is this, and u plus v and phi. Okay, so but we are not stopping at just first order in u and v. We'll keep expanding this up to second order in u plus v squared. So let me just write down this expression up to second order. But of course, we could separate this first order term into term involving u and also involving v. So I just do this. Okay, so let's take a 10-minute break. After the break, we continue. Okay, so expanding this up to second order. Okay, so let's continue. As I mentioned before the break, that we treat this u and v as small perturbations, and especially we consider the external potential due to the presence of a test charge q, which will induce some small density fluctuations, delta rho, which will couple to the Coulomb potential. And that's, that term induced by delta rho, we call this u delta rho. So the u delta rho is a small potential term, and this is the central term that we focus at the moment. But of course, we could also focus on v, but that's the next step. But the first step we study, because of the Coulomb term v, and this term is going to modify the small u term. Okay, so the key statement is that the v going to modify the u, and likewise the presence of u will also modify the v in the same manner. So when I say v modifies u, I mean because of the presence of v and the Coulomb potential, u is no longer just the bare u or the unscreened Coulomb potential, and we'll show later that this modification of u due to the presence of v will lead to precisely this Thomas Fermi shape screening effect. So the modification is to change the long-range Coulomb potential of u to the short-range screened Coulomb potential. And the reason that the u, the bare u becomes u effective is because the presence of other charge. Okay, so the other charge refers to the presence of v. So v is the Coulomb potential from all the remaining part of the electrons in your system, right? Remember that. And u is our focus. We would like to see, how much changes the potential u because of this small density variation, and that change of u should come from the presence of v. So this is the logic of this screening. As I mentioned, you could just use the cartoon picture to help you to understand this physics. As I mentioned, when you consider the Coulomb potential between any two charged particles. Do not forget there are many other charged particles standing in between. And you need to take care of that, all the different Coulomb potential which stands in between these two charged particles. And this is precisely this meaning of modification. And as U is no longer U but U effective, and the reason why U becomes U effective is because of V. So likewise, you could use the same logic that imagine that we consider a test charge which is just single electron, any one electron in V. Okay, and we study the presence of the external potential U, which will modify the V. Okay, in the same manner. So we don't repeat this derivation of second step, but we focus on the first step. The derivation of the second step is the same. So let's focus on the modification of U coming from V. So we applied the Rayleigh-Schrodinger perturbation, and this is the expression up to second order in U and V. So at zeroth order, the right-hand side is simply just fine. At first order, you get linear term in V and linear term in U, where I simply just focus on U, and therefore I circle with the red mark on U, and these last two lines refer to the second order contributions. So which is U times V or V times U. But you could check whether there's a UU term or VV term. Okay, so there are no such terms. So we only have this cross term. Okay, U, V and U, or U and V. So of course, we need to separate these two contributions, VU and UV, for a simple reason, because they are all quantum mechanical operators. The order matters. Okay, whether this V comes first and U comes later, or U comes first and V comes later, they're different in general. Okay, so we need to separate these two terms. But let me just circle again this U and U again. So when I circle those U terms, I really need to sum them up. I simply just sum up all the terms involving U. I only collect the terms involving U, and this is what I said. I only care about U effective. I don't care about V at this point. Okay, so if I define this U effective as just a bare value of U plus this V times U terms and U times V terms as a second order, then I could simply just write down the three terms. Okay, so I call this the bare U the term 1 because it's first order term, and the remaining two terms I call them the term number 2, but there are two subterms which I use this little I and double I referring to this two different second order terms. So if I define my U effective as a sum of the three terms, and I can simply just reorganize and simplify all this lengthy term on the left in just very simple form. Okay, if I only care about the U terms, and all the U terms now can be simplified as this single line here. And here is the U effective. You could just plug in this U effective back here, and you can show that they are simply just those terms. I did nothing but just organize all the terms and simplify this expression. But then we will show later that the U effective really plays a role as an effective potential, and later we'll see that this effective here really means that this is a screened potential. Meaning we not only consider this bare potential, but we also consider some inferences from the other charged particles that coming from V. So this is what I meant. The presence of V modify the Coulomb interaction U term. Okay, so the remaining job is to just expand this on the second order term, because this is just a trivial, right? This the bare term. So we just plug in the operator form of V and U, and then we simply just expand all these terms and we analyze the outcome of this many operator term. Okay, so let's take a short break. So again, this physics, this kind of derivation could be found in, say, David Pine's and also Kittel's second book, and you may also find some useful calculations in Flansburgh. But Flansburgh does not use the same type of perturbation that I introduced here. So this is kind of an old-fashioned quantum many-body physics. So again, the lecture notes by David Pine's are really, really useful. So it connects your quantum mechanics and solid state. Good. So let's just continue analyzing the first and the second term. So it looks really messy, but it is useful to use diagram again to really analyze the kind of a scattering among these 6 operators, right? 6 electrons. So we get 3 C daggers and 3 non-dagger C operators. At the end of the day, you will find that this becomes this following form. Okay, so some number times precisely the same form as this U delta rho. But this number here is no longer just 1 over q squared, 4 pi e squared of q squared, but something else. Okay, also should be included here. And we will see just a moment that this, the 6 operators could be so-called weak contract, or we could simply just use our knowledge to simplify the C dagger C to actually make a Fermi function-like number operator, and then we could, pull up all this modifications as a prefactor, which multiplies the density, this U term again. Okay, so this is called modification. Okay, correction, second order correction to this 1 over q squared long-range Coulomb force. And so we should go from here to here to really show that this 6 operators could somehow we could combine this, identify this momentum with that momentum, and so on and so forth. We need to actually kind of pair up 4 out of the 6. Okay, so we need to pair up 2 pairs of C dagger C, and then we'll show that the remaining operators, C dagger C, multiply U of Q, is our original U term, which means that this prefactor in front of this U should be the corrected or modified Coulomb potential for U. So this is the way to go. Okay, so let's just use a diagram to illustrate this. So we have incoming electron carrying momentum P, and from this U scattering, an outgoing electron carries momentum P plus Q, which is this. So we destroyed a single electron over here, and then we create another one over there by this U of Q interaction vortex point. Good. And what about the other 4? Well, we could also use another diagram. This is K and K minus Q prime and V Q prime, K prime, K prime plus Q prime. Okay, so another term consists of these 4 operators, 2 C daggers and 2 C's. So let's just do this correspondence. So you destroyed the electron state at K, and you destroyed another electron state K prime. You destroyed 2 electrons, right? And then they exchange momentum, which is Q prime. And then after scattering, the electron carrying momentum K becomes what? k minus q prime. And another electron carrying momentum k prime, when it is destroyed, the new electrons with momentum k prime plus q is created. Okay, so they exchange momentum by q prime. Okay, so now you should connect this 4 and the other 2. So the way that you connect these two subgroups of these operators is that you can identify this incoming electron state P here, the same as the outgoing electron k minus q prime over there. Okay, and also P plus Q state should be identified as this initial state k. So this red and yellow curves refers to the equivalence, okay, or identification. Okay, so meaning this electron state is the same as that electron state, or this electron state is the same as that electron state. So let's just list this identification. So P goes to P plus Q, and K goes to K minus Q prime, and K prime goes to K prime plus Q prime. But then you assume Q equals to Q prime, and P is the same as K minus Q prime, or K is actually P plus Q, right? So P is actually K minus Q, right? So if I identified Q is the same as Q prime, of course Q and Q prime are independent, right? But as I mentioned, if we don't have that identifications or simplifications, then we'll get no contributions. And this is the one of the two possible scenarios that will lead to the finite contributions. Okay, meaning the first assumption of this kind of a connection is this way. Okay, which I call this A. Of course, we can have different connections between all these lines, but we will just study this at first. So then we get such a identification. So P plus Q is actually K, and K is actually P plus Q, and P is actually K minus Q. All right, so if we make such an assumption, then we could simply just change the orientation of this contour without changing the topology of this contour, right? Or this kind of diagram. So you could clearly see that I could just make a loop. Let me just use another diagram first. This is P, and this is P plus Q, which is K, and K minus Q prime, which is P, and this is the V of Q, and K prime plus Q prime, which is K prime plus Q. Okay, so now you can simplify this diagram over here to that diagram if we assume this kind of a identification. Okay, suppose we assume this, and we could show that this diagram is the same, because now you can see that this P, when it hits the interaction U, and then it becomes P plus Q, and then you can identify this P plus Q as K, and then this is K, right? And then this this electron carrying momentum K then actually hit this interaction vortex V, and then it becomes K minus Q prime, but K minus Q prime is the same as K minus Q, and K minus Q is actually P. So K minus Q is actually P. So this is P. So you can see that this incoming electron over here on the left is the same as the outgoing electron on the right. So you could really complete the circle and form the loop. Okay, so you may not understand this rules at this point, but let me just say that without further explanation, and you will see why we make such a loop in the next semester. So we study the Green's function of solid state, and then we will introduce Feynman diagram, Feynman rules. At this point, what I want you to know is that when we make such assumptions and this incoming and outgoing electrons are reconnected and they form a loop. So let me just draw the final diagram. Of course, I could simply just change the position of this crossing point here. I could just invert this to anywhere I want. I can simply distort, rotate the diagram as I like, but without changing the physics. Okay, so that's the benefit of this diagrammatic representation of the kind of a complicated interactions. So let me just put this UQ up here, and you form the loop made of these two electron states. One is P, another is P plus Q. And then at bottom of this loop, you have this VQ interaction. And then at the very bottom, you get two electron states, one incoming carrying K prime, another is K prime plus Q. Okay, so I simply just close the loop and form a really perfect circle, and then make an upturn of this U of Q, and then I flip this U of Q to the very top, and then this circle in the middle, and then I could extend this kind of a kink like two lines as a straight line in the bottom, and this is the final plot. So they are all equivalent. But when I draw the diagram like this, and there's a very, very special meaning or very important meaning, is that remember when we study the modification of the U of Q, and you can compare the original diagram of U of Q, which is what? Which is one electron come in and go out, and they exchange momentum with U of Q, right? As a bare interaction. So this is a bare U interaction. This is simply just small charge density, delta rho, coupled to the Coulomb potential, right? So that's the original bare interaction, and we use the diagram to illustrate such the bare Coulomb potential or U term. But here I could simplify this second order perturbation, and I could use a complicated diagram. But if I simply just put everything inside the red box, and I could show to you that this is more or less the same diagram, except now there's something in between this interaction vortex. Okay, so if I simply just block the object inside the red box, and I don't want to know what this is, I just want to know that I just want to express that there's something that in between this bottom line and this interaction vortex cross. Okay, so if I remove this shaded circle, and I got exactly the same type of interaction, right? So they are equivalent if this stuff is gone. Do you see that? You just look at the diagram, and they are very similar if I draw this diagram the same way. So the only difference between the bare interaction and the modified one is that the modified one shows some complicated object in between this interaction and this electron so-called propagating line. But if I simply remove this bubble or the ring in between, and this diagram is the same as the bare one. So which means that indeed this diagram modify the U. Okay, so this proves that the presence of this red box indeed modify the U, the bare U. Because if I remove this, meaning if I make this, this circle, the box, just 1, okay, just constant 1, and there's no modification. And this is called a corrected interaction vortex for U is the same as the bare one. But of course, this is not 1 because this bubble, we need to take care of this calculation. Okay, so we have not done the calculation, but somehow we know this picture globally, meaning that as long as we can calculate this diagram inside the red box, and we know how to modify this bare U because they share the same structure of interaction. Okay, so that's something between is really the effect coming from the other charged particles. Okay, so which we will take care in just a moment. Okay, so any questions so far? This is really important. You may not 100% understand this diagram, but once I plot this diagram, you get a general picture. And what we are going to do is to use perturbation theory and to calculate this shaded area or the red box and to really correct or modify the on-screen Coulomb potential. And this is the source of the screening effect. This leads to the screening. Of course, this is just one diagram. We have many diagrams we need to sum over, but let's just do the simplest one, and then all the other diagrams are simply just the same diagrams that repeatedly are present, and we need to sum over all the diagrams that show the similar geometry like this. It's called the ring diagram. And later we will call this summing over all such a ring diagram, this RPA, the random phase approximation. And we will illustrate this in the diagram, in a diagrammatic way later. Okay, we sum over all this ring diagram. And when we sum over all such a ring diagram, and we will get a full screening effect. Okay, let's go to the other possibility where Q is said to be minus Q prime. So this is another contribution which leads to the same diagram as the term A, and you can show that when Q is minus Q prime, and you could identify all this initial final state of those electrons, and in particular we can identify P plus Q as K prime, and therefore P is actually K prime plus Q prime because Q is minus Q prime. So in this identification, we can show that this diagram is the same as A, and therefore we sum over this contribution from this A scenario and the B scenario, and you get a factor of 2 because A is the same as B. And then you need to just calculate this bubble diagram, a single bubble diagram. And also you could use this identification to show that 6 operators, when you make such identifications, you can show that you can form this electron number operators. Remember, this will become the Fermi function when you evaluate the expression, and this is all we want. We want to reduce these operators to the number operator. And this epsilon 0 minus H0 inverse operator, when you act on this state on the right or left, phi 0 state, you'll get this factor, which is the energy of intermediate state, epsilon 0, which is epsilon p. It is the kinetic energy of non-interacting electrons, and minus epsilon p plus q is again is a non-interacting electron kinetic energy from this h0, but you subtract this 2 and you inverse that. And at the end of the term, you get again this u of delta rho. And this is something that I said earlier, that you could show that this complicated 6 operator term could be reduced into the same form as the u delta rho multiplied by some modified number, which is this stuff. And this stuff is the stuff that I mentioned earlier, that this is the correction to the bare u. So we need to really calculate this thing. But this is just the first and the second order term, which shows the u appearing first and v later. Okay, so you could calculate this, this third term, which is another second order term, where you have v first and u later. And at the end of the day, you will get these contributions to u effective, which is really similar but slightly different. Sum over k q. So again, this is the standard u delta rho, the same form as appearing in the Hamiltonian, but you get a very similar but slightly different prefactor, which I call this shaded triangle. Okay, so let me just sum up all the terms. The u effective is the u bare plus the red circle, shaded red and the shaded triangle, right? So let me just simplify this term. When you really sum over this 2, you get the subtraction. You get the cancellation between some terms. All right, so unavoidable. This is your homework, and also this is your homework. But of course, once you can prove this 2 expressions, and you simply just sum over this 2, and especially order between, say, mp and 1 minus mp plus q is different, right? So in the first term, blue circle, mp appears on the left, and on the right, this is 1 minus mp plus q. But down here, the momentum indices carried by this occupation number operators are different. So here, factor m appear on the left carry momentum p plus q instead of p. And inside this bracket, 1 minus n here, as momentum indices are different, this one is p plus q, but the bottom one is p. So you simply just interchange between p and p plus q, and you can convert from one to another. Okay, so when you sum up all these 2 terms, you get this direct sum of these 2 brackets, and therefore you immediately see that there's a cancellation of this cross term. So now the correction is really simplified as this: mp plus q minus mp u plus dot dot dot. Okay, so here this mp is actually the expectation value of this mp operator. Whatever this stays on the left and right, sandwich this mp operator, you always get a Fermi function. So here we simply just use a Fermi function for this number operator, because at the end of the day, we need to sandwich this operator, and whatever state that we sandwich, it always gives us the Fermi function. Okay, so time is up for the day, and let me summarize. So we derive the corrections to this Coulomb potential U coming from this, this small density fluctuations coupled to the Coulomb potential, and then reduce this to the bubble, and we will analyze the other diagrams which consist of many, many bubbles. Okay, so I'll see you next Monday.